I just wanted to spend a little bit of time talking about the importance of learning the multipole expansion technique. I've heard of it before, mostly in regards to planetary magnetic fields, and that's a slightly different application. We're actually going to learn about this when we learn about magnetostatics instead of electrostatics. Right now we are applying the multipole expansion technique to electric fields, but you can apply this technique to magnetic fields and also gravitational fields or even temperature fields. You can apply it to a lot of different things, and the fundamentals are the same. So, for example, the Earth is just a simple graphic from hyperphysics, but you often learn that the Earth's magnetic field is dipolar, which means it looks like the same kind of magnetic field that would be produced by a bar magnet. But this really is only true if you're far away from the center of the Earth, okay? So if you're far away from the Earth or a lot of other planets, their magnetic fields look dipolar because that dipole term is the leading term in their multipole expansion of the field, and it is the strongest term. It's the term that falls off the least sharply with distance. So if you get far away, then that dipole term is going to dominate and the field looks like a dipole. But if you get closer to the point where the magnetic field is generated, some of the other higher order terms like a quadrupole term or an octupole term is going to get stronger, and you're actually going to start seeing deviation in the field from just a regular dipole field. And when people actually model planetary magnetic fields, they model them in terms of the coefficients that go in front of these different multipole moments, okay, that we're going to talk about when we talk about electric fields. Another example of that that's quite a bit different but still related, this is the cosmic microwave background radiation. This light was emitted when the universe first became transparent to light, which is what happened when the electrons and protons that were formed after the Big Bang combined together to make hydrogen atoms. But anyways, it's really old and it's cold and redshifted because it's been stretched by the expansion of the universe. But all of these little fluctuations in the temperature can be modeled with what's called a power spectrum, which actually means this is what you're looking at. This is multipole moments down here. And this is kind of like a power or a strength. And so you can see they've got to very high numbers of multipole moments because this is such a complicated map. It's not really like a dipole, which is quite simple. But this gives you the strength of the coefficients that are in front of particular multipole expansion terms. And when you add them all together, you can get model something that looks like the cosmic microwave background radiation. Here's an example from electrostatics. So these are electric fields that look like a dipole from far away. This here is an actual true dipole, so it's worth looking at. This is what a real dipole would look like. You would only get this kind of field if you take the separation of the charges and pull it all the way down to 0. So this is the only real dipole. And of course, that doesn't really happen in real life, but mathematically you get an actual true dipole field even near the charge here if you take D down to 0. If there is some non-zero D, so this would be like a true physical dipole, okay. Here you can see that if you're close to the charges, right, where your distance from the charge is not very large compared to the separation, this actually doesn't look that much like what this dipolar field looks like close to the center, close to the origin. But if you get far away, if you're over here, okay, then it does look quite a bit like the dipole field. And the further you get away from the charges, the more it's going to look like a true dipole, okay? So this only looks like the dipole at R is much, much bigger than D. Okay, and then these are some other examples. This obviously doesn't look like a dipole. close to this polarized disk, but if I look far away, you can see that the dipolar part of its electric field is dominating because it does look quite a bit like a dipole. And then same thing for a capacitor. If I'm close, it doesn't look like a dipole. If I'm far away, then it does. Okay. So the point is that there's lots of things that actually act similar to this dipole, and as long as we're sufficiently far enough away from them, then we can model their field to be basically a dipole. It's not going to be exact, but it's a good approximation. Another example, and I like this because we talk about this in astrobiology, which I'm teaching next quarter, is a water molecule. So this right here is just a water molecule, H2O. Because oxygen really likes electrons, it actually pulls the electrons from the hydrogen atoms. It's an ionic bond, okay. And for this particular bond and the configuration of the molecule, the fact that it's got this bend in it, it means that this part of the molecule, the water molecule, where the H atoms are, has a net positive charge, and this part with that is where the oxygen atom is, has a net negative charge. So we would say that this molecule is polarized because it has a different charge on this side and that side. This polarization makes it a really good solvent because these electrical charges, or these net charges on the different parts of the molecule, actually cause it to make good bonds, not only with other H2O atoms, but with other types of molecules, which can help dissociate those molecules. So for example, salt, which is also an ionic bond between sodium and chloride, it's easily pulled apart by water because of those electromagnetic forces, which is what happens when you dissolve salt in water. Okay, another example of a couple of dipoles, or things that we can model as dipoles. We had our conductor in a static electric field. This can also be modeled as a dipole, or it's going to look dipolar far away. In this case, we've got a positive down here and a negative down here. In this case, though, it's going to be the field from the conductor only. Which would need to be added to the external field. Okay, one more example. Even if you just have an insulator, so an insulator is an object where charges are not free to move around like they are in a conductor. Charges are confined to the individual atoms, but even an insulator can get dipolar when there is an external electric field, and that's because you can actually shift that electron cloud around. So if this is the electron cloud around a nucleus of an atom, and this was that positive nucleus, if this was in an external field, it would shift the positive charge relative to the electron cloud like this, and that would give you a net positive down here and a net negative down here. Okay, and the separation of charges would produce a dipole even though the atom is net neutral.